Amazon S3 is perhaps the most successful distributed system ever built. It manages over 100 trillion objects and handles tens of millions of requests per second. But to achieve this scale, S3 had to break the rules of traditional computing. In a standard file system, like the one on your laptop, you can open a file, change a single byte in the middle, and save it. S3 doesn't allow this. S3 is an object store, not a block store. Every time you edit a file in S3, you aren't actually changing the original data. Instead, you are creating an entirely new version. This is the magic of the append-only model. By treating data as immutable, S3 eliminates the complex locking mechanisms that slow down traditional databases, allowing it to scale nearly infinitely across hundreds of thousands of hard drives worldwide. When you look at the S3 console, you see folders. You see images, backups, and logs. But here's the secret. S3 has no concept of folders. It is a flat key value store. In a real file system, a directory is a special file that contains pointers to other files. In S3, the folder is just part of the object's name or key. When you store a file at images/vacation/beach.jpg, S3 sees that entire string as a single unique identifier. This design choice is critical for performance. Because it's a flat map, S3 can use a distributed index to find any object in constant time, regardless of how many billions of objects are in your bucket. It doesn't have to crawl through a directory tree to find your data. It simply looks up the key and returns the bytes. This is why listing a directory with millions of files is often the slowest operation in S3. It's essentially a prefix search on a giant list. To understand S3's performance, we have to look at how it handles writes. S3 is append-only. This means once an object is written, it cannot be modified. If you want to change one word in a 10 GB text file, you must re-upload the entire 10 GB. This sounds inefficient, but it is the cornerstone of S3's reliability. Because objects never change, S3 doesn't have to worry about data corruption during an update. There is no partial write state. A put request is atomic. Either the new version is fully stored and acknowledged, or the old version remains untouched. This immutability also makes caching incredibly simple. Since an object with a specific version ID is guaranteed to never change, S3 can cache it aggressively across the global AWS network without ever worrying about the cache becoming stale. It's a trade-off. We give up the ability to do random access writes in exchange for massive, reliable throughput. S3 guarantees 11 nines of durability. It's not by just making 3 copies of your file. That would be too expensive at scale. Instead, S3 uses a sophisticated technique called erasure coding. When you upload an object, S3 breaks it into multiple shards. For example, it might turn your file into 10 data shards and 6 parity shards. These 16 shards are then distributed across different storage nodes and even different physical data centers, known as availability zones. Because of the mathematical properties of the parity shards, S3 can reconstruct your entire file, even if several of those storage nodes fail simultaneously. It's like a Sudoku puzzle, where you can lose half the numbers and still solve the whole grid. This allows S3 to survive the loss of an entire data center without you ever losing a single byte of data. It is the ultimate insurance policy for the world's data. For many years, S3 was eventually consistent. This meant if you overwrote an object and immediately tried to read it, you might get the old version for a few seconds while the change propagated. However, in late 2020, AWS achieved a massive engineering feat. They moved S3 to strong consistency. Now, as soon as a put request is successful, any subsequent GET request is guaranteed to see the latest data. This is incredibly difficult in a system as large as S3. It requires the metadata layer, the part of S3 that knows which physical disks hold your shards, to be perfectly synchronized across multiple regions instantly. By achieving this, S3 became a viable storage backend for data lakes and big data tools like Spark and Presto, which rely on seeing the most recent version of a file to maintain data integrity. In summary, S3 works by embracing constraints. By giving up the features of a traditional file system, like nested folders and partial writes, it gains the ability to provide virtually unlimited capacity and incredible durability. It treats your data as immutable objects, protects them with erasure coding across multiple zones, and provides a simple key-value interface that scales with your needs. Whether you are storing a single-family photo or a petabyte-scale data warehouse, S3's append-only magic is what makes the modern cloud possible. Understanding these trade-offs is key to building resilient, cloud-native applications that can stand the test of time.